All right, hi folks. Today we're going to look at a new skill, a new test. And before we get into that, I'm going to just want to remind you about something that we've done in the past. So do you remember back when we were doing t-tests for population means, and we had to ask this question, are the population variances equal or are they not equal? And at the time we just said, okay, well, they're either not, obviously not equal, or if they are equal, it's because the sample variances are really close and there's reason for us to believe that they're really the same. Okay, well, now we're going to expand on that, and we're actually going to be able to do a test here that's going to tell us whether the population variances really are the same, if one's greater than the other, or so on. So we're calling this comparing two variances. We have two populations, two variances. We'll have samples, which will give a sample variance, and we'll use those sample variances to determine whether the population variances are equal, not, or so on. So this is a new type of distribution that we're going to use. It's going to remind you of our chi-squared distribution, but it's called an F distribution. Okay. So if we take a look at the graphs here, again, this should remind you of that chi-squared graph. Now it's going to depend on the degrees of freedom. What's different about this is that there's actually 2 degrees of freedom, because we set up our F distribution as a fraction with a numerator and denominator. Now we're going to have S squared, okay, sub 1, be the sample variance, okay, and it's going to be the larger of the two, right? So we've got a population variance, and remember that we write that population variance as sigma squared here. So we have this first population with its population variance. We have a sample from that. S sub 1 squared is the sample variance. And we have the same thing for a second population, which has its own separate variance. And we just choose it so this one's larger. And the reason that we do that is if we pick S sub 1 squared to be the larger of the two, what's going to happen with our fraction? Well, this is always going to end up being greater than 1 when we take a look at this, which means that we're always going to have a positive distribution. So when I said there's 2 degrees of freedom, that's because we have a degrees of freedom from our first population and our second population, and this is what we're going to call it, df sub n. So the degrees of freedom from the n stands for numerator. I have a typo down here. The second one is for the denominator. That's what the D stands for. So we have 2 degrees of freedom that determines which of these distribution curves that we're looking at. So it's this big family, and our degrees of freedom from the numerator and denominator will help us find that. As it says up here, the tables for this are in the back of your book in the appendix. There's several pages. If we find these here for you. So take a look here. And the way that we see this happening is that we have a degrees of freedom for the numerator, which goes across the top, and degrees of freedom for the denominator, which goes along the side to help us identify the point that we need. The reason that there are several pages is because now each level of significance has its own table, because we do this degrees of freedom of the numerator, degrees of freedom of the denominator, and we do this kind of thing on the chart to locate it. So each level of significance will have its own table. So make sure that you get familiar with that. All right, so how do we do our test? Well, our conditions are the first thing that we should ask ourselves. Our conditions are that both samples must be random, they must be independent, and each population must be normally distributed. Wouldn't make sense for us to compare variances of populations that have different types of distributions. If one's a normal distribution and one's a uniform distribution, one's a normal distribution, wouldn't make sense for us to say, well, does the one have a larger variance than the other? Okay, they're totally different types of distributions. So this only works for populations that are both normally distributed. So remember, each population has a variance. Okay. That's what those are, sigma squared, population 1, population 2. Those then are going to be worked with by looking at a sample variance, s squared sub 1, s squared sub 2. Remember this, I said on the last page that we're going to let the variance from the first population be the larger one. Our test statistic, like we saw on our last page, is going to be the larger variance, sample variance, over the smaller sample variance. Our degrees of freedom from the numerator and denominator are both found by taking the sample size minus 1. Okay, so we don't have to have the same sample size for this. Let's say that this has a sample size of n1 and this one has a sample size of n2. The degrees of freedom for the numerator would be n1 minus 1. Degrees of freedom for the denominator would be n2 minus 1. Okay. So let's get to a problem here. So let's say a medical researcher claims that a specially treated intravenous solution decreases the variance of the time required for nutrients to enter the bloodstream. So we've got some solution. We want to know, hey, how long does it take for the nutrients that are in the solution to enter the bloodstream? Now, we're not looking at the mean length of time. We're talking about the variance. What does that distribution look like? Okay. Now, the researcher here is claiming that this new treatment solution has less variance than the old one. It says it decreases. I did not spell that right. Get that S out of there, typo. It decreases the variance compared to the normal solution. So independent samples from each solution type are randomly selected. Another typo, I'm sorry guys. With the results below. At a 1% level of significance, is there enough evidence to support the researcher's claim? So here is the normal solution. Here's the new one, the new treated solution. So, okay, what's our test? Well, let's make sure our conditions are met. So if we look back at what our conditions are, both samples must be random. We see that independent samples from each type of solution are randomly selected. So we have the random portion. Secondly, these samples must be independent. And it says the samples are independent. Okay. The outcome of one of the samples is not going to influence the impact of the other. Okay. And our third one, I don't see in here, right? So okay, we're missing this one. Okay, so we don't know that the populations are actually normally distributed, that the old solution has a normal distribution, and that the new one has a normal distribution either. So if that's the case, we wouldn't be able to do this problem. But like we've done many times in class, now that I've made sure that you're checking the conditions, we'll actually assume that they are true. Populations are normally distributed. So normal distributions. Got it. Okay. Now, part of what we have to do here is we have to remember this piece, okay, that we need the sample variance from the larger sample variance to be our numerator. So notice I didn't have this labeled, okay, and as we take a look at the sample variances, this one is clearly larger, so we're going to call this our first population. I'm going to put 1s there. This one's smaller, so I'm going to put 2s there. Now, we don't know what the actual population variance is for this one or for that one. But the medical researcher is claiming that the new treated one decreases the variance compared to the old one. So let's write our hypotheses. The claim is that the new one decreases the variance. So the new one is the treated solution, okay, and the claim is that it's going to decrease compared to the old one. Okay. So just like before, we want to always put our 1s on our left and our 2s on our right. So if the new one, which is the second one, has decreased the variance, this needs to be less than that. So this is our greater than sign, and that's our claim. Our null hypothesis would then be that the first one is less than or equal to the variance of the second. And I forgot my squareds here because these are variance. Okay. So again, to rehash that, just like we've done in the past where we've had two samples, let's always put one on the left, two on the right. Let's look at our claim. The claim is the new one is less than this old one. So I set this one up and I wrote the inequality so it's less than the first one. So there's our hypotheses. Now, how are we going to run our test? Well, we need a test statistic right here. So let's find our test statistic, which is going to be S1 squared over S2 squared. So that's 180 over 56, which is let's see here, does that reduce 45 over 14, which is about 3.214. Okay, so we have our test statistic. Now what we need to do is we need to find our critical F-score to set our rejection region. Now, how do we do that again? Well, remember that there are 2 degrees of freedom and we're going to have to use our table. So what is the degree of freedom from our numerator? Well, our numerator was from population 1, which had a sample size of 25. So that's 25 minus 1, which is 24. Degrees of freedom from our denominator, okay, which had a sample size of 20, is 20 minus 1, which is 19. So we have our 2 degrees of freedom. We have our level of significance at 1%, so 0.01. So now I'm going to go to my book here, okay, and my table to find that. Make sure that you're on the right table where the level of significance is 0.01. For me, that's on A21. I am going to look across the top to find 24 degrees of freedom. I'm going to go down the side to find 19 degrees of freedom. And I see 2.92 is our critical F-score. So if we were to draw this distribution, remember it's skewed to the right, it's all positive. So remember it's going to look kind of like this. Okay. Our rejection region is set at 2.92 for our critical F-score. Our test statistic, RF, is at 3.214, which is in the rejection region. So we will reject the null hypothesis. There is enough evidence to support the researcher's claim. And there we go. So, rehashing, make sure your conditions are met. Write your null and alternative hypothesis. Always put your 1s on the left, your 2s on the right. Calculate your test statistic F by taking the sample variance of the larger over the sample variance of the smaller. Find your degrees of freedom with your level of significance to set your rejection region with your critical F-score. Draw out your distribution. We found that was in the rejection region. We rejected the null hypothesis. Come on, lights. Turn back on. And make your conclusion. So that's how our 2 sample variance test works. Thanks for watching.